So hi all, my name is Malcolm Bernard and I'm a marine sciences graduate student at the University of North Carolina at Chapel Hill's Institute of Marine Sciences. Welcome to the first seminar in the Eastern North Carolina section of the American Chemical Society Diversity in the Chemical Sciences seminar series, which is funded by a local section sustainability programming grant from the American Chemical Society Committee on Environmental Improvement. Before I introduce our incredible speaker for today, I wanted to talk about a few Zoom seminar housekeeping items. Firstly, we are recording the seminar, and recording will be available following the webinar. The exact timing on that is to be determined, but it will be available. We are also live streaming the seminar on the UNC Institute of Marine Sciences Facebook page. If you have any questions for our fantastic speaker, please type your questions into the Q&A portion below, and they will be answered at the end of the seminar. Additionally, a form should be available through, I'm not sure if it's already available or at the end of the seminar, should also be available. Please fill it out as it will help us as we continue on this series, and also as we do some reports to the local, or to the Committee on Environmental Improvement. Without any further ado, it is a great honor to introduce today's seminar speaker, Dr. Joseph Francisco, who is the President's Distinguished Professor of Earth and Environmental Science and Professor of Chemistry at the University of Pennsylvania. Dr. Francisco graduated with a Bachelor's of Science in Chemistry from the University of Texas at Austin in 1977, and with his PhD in Chemical Physics from the Massachusetts Institute of Technology in 1983. He did postdoctoral studies for 2 years at the University of Cambridge in England. During his illustrious career as an atmospheric chemist, Dr. Francisco has published over 600 journal articles and book chapters, co-authored the textbook Chemical Kinetics and Dynamics, was appointed by President Barack Obama to serve on the President's Committee on the National Medal of Science from 2010 to 2014, and is a past president of both the National Organization for the Professional Advancement of Black Chemists and Chemical Engineers and the American Chemical Society. Additionally, Dr. Francisco has received numerous accolades for his incredible work, including election to the U.S. National Academy of Sciences in 2013 and the American Academy of Arts and Sciences in 2010, my apologies, a Guggenheim Fellowship, a Sloan Fellowship, an Alexander von Humboldt U.S. Senior Scientist Award, and becoming a fellow of the American Physical Society, American Association for the Advancement of Science, and American Chemical Society. Today, Dr. Francisco will be talking with us about water effects on atmospheric reactions. Please welcome our seminar speaker, Dr. Joe Francisco.
Thank you, Malcolm. Thank you for that wonderful, introduction. I'm sorry you guys are experiencing such rainfall, but rain is water, and that's kind of appropriate for the talk and looking at water effects on atmospheric reactions. I want to kind of talk a little bit about some of the motivation of why we want to consider that. For the longest period of time, we were really kind of interested in chemistry up in the stratosphere. And the reason why we're interested in chemistry in the stratosphere, because we were interested in how the effects of chlorine and the effects of chlorine and the destruction of ozone, and how is that chlorine chemistry, details of that chlorine chemistry define the chemical pathways and mechanisms that play in the creation of the ozone hole. One characteristic of the stratosphere, it's a very dry region of the atmosphere. When I mean dry, uh, not very much water. In fact, um, very little water up in that region. And I kind of like to think of chemistry in the stratosphere as really kind of being very pristine chemistry. However, right, because of global warming, you can say global warming and climate change, consequence of that is a lot of the oceans are heating up, and because of that warming, there's increasing, water vapor going into our atmosphere, from the oceans. And of course, there are convective, wind currents that are moving that water vapor into the stratosphere. And so, one of the questions that we've been intrigued by, because if you look at all the atmospheric models, many atmospheric models that represent the chemistry in the stratosphere don't have water in them. And that kind of caught our interest, and we wanted to kind of explore what is the impact of water on chemistry in the atmosphere. As I said, when we look at atmospheric models that kind of represent that chemistry, and this is one kind of a small atmospheric model that's kind of used to look at ozone perturbations, you don't really see, the impact of water on, any of these reactions represented here. Now, what you will see um, here is the reaction of oxygen atoms with water, and that reaction gives OH radicals, which are really actually that's represented here, and that's really important in terms of generating OH radical, which is a very important atmospheric oxidant that is used to clean up a lot of the organics that are emitted into the atmosphere. So you can see there are a whole host of reactions here that certainly taking place and certainly being modeled to take place in the stratosphere that impacts ozone profiles. So the question is, what is the impact of water, on that chemistry, if any? And that's kind of the kind of simple question that we went after trying to look at. Now, I can go and look at water effects on all those reactions, but we wanted to kind of be somewhat strategic in our examination of this question, and because there's many different reactions to kind of pull from. But what we wanted to kind of do is go back and look at where water may couple the most, and what would be the impact of water and critical intermediates, in that chemistry and in the coupling of that chemistry. And the one that we want to kind of take a look at is odd oxygen chemistry of hydrogen. So, and the critical species are OH and HO2. Just to kind of give a brief overview of why that chemistry is important. How OH radicals, which, as I stated earlier, turns out to be a very important atmospheric oxidant that drives the oxidation of a lot of the organics. How that species is produced is by reaction of O singlet D atoms with water. And O singlet D atoms come from the photolysis of ozone. And this reaction, oxygen atom with water, accounts for about 80% of the production of OH radicals in the atmosphere. Once those radicals are produced, they actually start to oxidize CO to give CO2. This turns out to be one of the most important reaction steps in the conversion of CO to CO2 in the atmosphere. in the process producing hydrogen atoms, which are scavenged up by O2 to give HO2 radicals. And HO2 radicals can react with NO or react with ozone to go back and give you OH, and you got a nice little cycle here. Or HO2 can self-react with itself to give hydrogen peroxide, and its photolysis will give you OH. And we kind of think of hydrogen peroxide, H2O2, as kind of a sink or reservoir for OH. And this self-reaction here of HO2 plus HO2 actually accounts for about 15% of the recycling of the HO2 back to OH. And so what we're going to do is look at how water might interact with these two critical species, and then how does it really change some of the chemistry. Now, motivation, another piece of motivation, why it was strategic to kind of look at this, came from some work, some field measurements work, and some modeling work that was done. And and some field measurements work, and this actually came off some field measurements looking at OH and HO2 off Oki Island in Japan, where they sent some balloon measurements out, and the instruments were really calibrated to make measurements of HO2 radicals. And so it was well calibrated, for those measurements. And you can see the measurements here. And of course, now the question is, with all the chemistry that we know that can account, for the production and loss of HO2 radicals, can that chemistry model what is observed? And this line here kind of represents, if the model and the observations were in agreement, everything would kind of fall along this line. But what you can see, the observations are really significantly falling away, from what is calculated, suggesting that, and the models were suggesting that the HO2 really, the models were overestimating HO2, which suggests that there was some real missing chemistry in the models to account for the HO2, or even OH for that matter. Some experiments coming out of JPL actually pointed to some exciting new direction, and maybe some explanation behind the observations, and maybe some insight into perhaps some of the missing chemistry in the models. So what our colleagues, my colleague Stan Sander, did was some beautiful experiments looking at the HO2 plus HO2 self-reaction. And it's kind of well known in the literature, prior to Sanders' experiments, but that reaction fundamentally is a three-body reaction. And there have been a lot of measurements on that reaction in the presence of third body, and in that third body was usually N2, since that is a significant quantity of N2 in the atmosphere, also with O2, and also with buffer gases, inert gases like argon. And when you look at the kinetics of that three-body reaction involving HO2, you get the right kind of kinetics, and nothing new, nothing surprising. However, what Stan realized, that in the atmosphere, you have a significant quantity of water. And what is the impact of water vapor on this self-reaction? And of course, when he started to study that, he saw some very interesting, unusual, behavior. Um, and one of the behaviors you start to see that the rate for that reaction was highly dependent upon water. Uh, and so rates, if it's a true, elementary reaction, should be really independent upon the concentration profile of any of the reacting species. But in this particular case, he saw that there was a water dependence, and you can see the water dependence at every given temperature, for this reaction. But what was really counterintuitive about the measurements was that he started to find that as you lower the temperature of his reaction cell, that the the reaction started to accelerate, and that kind of goes counter to what we've learned in basic physical chemistry. As you raise the temperature, reactions and the rate of reactions accelerate. When you lower the temperature, the rates of reactions, get slower. And in this particular case, as you're lowering the temperature, the reactions are accelerating as much as by a factor of 25. So what was the explanation? Clearly, it's truly not simple three-body kinetics from an elementary process. And so in order to kind of explain the data, what the JPL group proposed was that the HO2, when it encountered the water, it actually formed an HO2 water complex. And now it's this water complex that reacted with the other HO2 to give you the observed products of hydrogen peroxide, O2 plus water, or the complex could self, react to ultimately give you that. And of course, he can fit all the experimental observations, to this mechanism. Um, Now, one of the things that was fascinating was some modeling studies done by Stockwell that was published in JGR back in 1995. Uh, and what was published in 1995 by Stockwell was where he showed that if you kind of do an air quality modeling and and you add the water effect as a as actually dictated by the HO2 plus HO2 self reaction. One of the things that you found was that the models, by looking at the differences of the models with and without water, you can see differences anywhere between 55 and 70%. But as you went up in the atmosphere, those differences actually kind of reduced significantly. And that kind of made sense because as you go up in the atmosphere, the water profile actually drops off, and the real dependence of the water, significantly drops off, and you see that. But what it says is that in the lower region of the atmosphere, the water dependence, at least on that one reaction and how that one reaction propagated, errors through the models was really quite significant. So the question was, does an HO2 water complex exist? Now, the JPL proposed a model, proposed a mechanism to explain their experimental observations from the laboratory that an HO2 water complex existed. And we were asked by the JPL group if we can actually show or prove or disprove whether such a complex existed. And at that time, one of my graduate students had actually did the calculations and showed that the HO2 water complex actually exists as a double hydrogen bonded complex, where you actually have a very, very strong hydrogen bond of the hydrogen from the HO2 with lone pairs of the oxygen of the water. And you also kind of got a little bit of some typical hydrogen bonding interaction between the oxygen, the terminal oxygen of the HO2 carrying the lone pair electron with that of the water. The total effect of this interaction that resulted in the binding energy roughly about 6 kcals. Why is that significant? Why I mentioned that? Because initially what we kind of did was treat the HO2 water complexes kind of in the same structural fashion as water dimers. So we took this terminal oxygen here, replaced it with a water, I'm sorry, with a hydrogen. So you get water dimer. And we know with water dimer, the binding energy is roughly about 4.9 kcals. But replacing that hydrogen with oxygen to get the HO2 water complex, what we saw is not one hydrogen bond that was important, but two hydrogen bonds, a double hydrogen bonded complex, but with a binding energy close to 6 kcals. This figure here actually came from the experiment done by Indo, which actually validated and confirmed the calculations that my student had done. And he too observed the binding energy roughly around 6 kcal. So that was kind of significant. But as my colleagues would say, that's a laboratory experiment. Uh, does an HO2 water complex exist in the atmosphere? And if so, where and what does it look like, and what are the impacts of what is the impact of its existence in the atmosphere? Well, that's where some of the first excitement came about, because with that experiment, and my student did some experiments at JPL where they measured the equilibrium constant between HO2 and water. And having measured that equilibrium constant, if you know how much water vapor you have and you know how much HO2 you have, you can now actually figure out how much HO2 water complex you would have. And this is kind of a profile of the HO2 water complex up in the atmosphere. And actually, one of the things that we found was that profile is going to be largely governed by the water vapor profile down in the lower region below 15 kilometers, hence down in the troposphere. But the profile of the HO2 water complex, and that was really kind of surprising, is that about 30% of the HO2 is tied up as HO2 water complex. So now one of the big questions that the atmospheric scientists and measurements people were really trying to get a handle on was was all our man-made activity. How was that activity, impacting the oxidative capacity of our atmosphere? And of course, the answer to that question is how much OH or HO2 you have, and is that being impacted? But if all the instruments are been tuned to looking at OH and HO2, do you really have a good handle of the oxidative capacity that the atmosphere have when you're missing about 30% of the budget, because that budget, that 30% of the HO2 is tied up with water. So the excitement around that discovery actually motivated some of our colleagues to kind of look at whether it was just truly just unique to HO2, or whether there are other kind of peroxy radicals or organic peroxy radicals that too can actually be complex. And if they were to be complex, where are they located? And so the answer to this is some modeling studies by our colleague Dudley Shirley-Walter at Bristol University, where he actually showed that there are other RO2 radical species, peroxy radical species that are complex with water, and that complexation can range anywhere from 18 to about 6 to about 12%. Some of the new modeling studies are finding high percentages, but the bulk of the location is around in the tropics, around the equator, where you kind of see very high water vapor profiles is where you see significant water complexes being formed. But this raises some interesting new questions from a chemistry standpoint in terms of looking at reactions. And let's go back and look at just the HO2 plus HO2 reaction, in the sense that what it means is now, instead of this reaction just happening going across a barrier, what happens now to this reaction when there's a complex that's actually formed, and how does this complex change the course of the reaction? And is there a possibility that the change of the course means a change in distribution of the kinds of products that you see as a result of that complexation? So this created some excitement looking at this question, and what is the role of complexes in atmospheric chemistry, and and what is the influence? So I like to kind of pick on this reaction, OH plus HCl. And the reason why I kind of like to pick on this reaction, because HCl tends to be a sink for chlorine in our atmosphere, and this is how, you know, chlorine is taken out of the catalytic cycle for the destruction of ozone by its reaction with methane to produce HCl. And HCl is quite hygroscopic, and so, you know, a fair amount of it is kind of taken up in clouds. People have wondered if photolysis of HCl would reintroduce that chlorine back into chlorine cycles, but photolysis do not, because you can't really get 155 nanometers down in the stratosphere, even in the troposphere. So this process, photolysis of HCl, becomes really quite insignificant. Now, what's a possibility is that OH radicals can actually extract off the hydrogen from HCl, producing water, and reintroduce that chlorine. But it's kind of well known that that reaction, from all the experimental studies, is kind of moderately slow, and it's not fast enough to really have any significant impact on reintroducing that chlorine back into the chemistry. And of course, theoretical studies mapping out a good potential energy surface for this reaction kind of support those experimental measurements for the rate for this process. And the description of the potential energy surface that describes the kinetics is as follows. So you have OH. The OH attacks this hydrogen, forms kind of a pre-reactive complex. There's a barrier about 2.1 kcal, and this is what the transition state looks like as it goes off to give water plus Cl in a post-reactive complex. And of course, that then separates out to give you the chlorine plus water. So there's a modest little barrier, about 2.1, and that 2.1 kcal barrier is kind of explains why you get that slowness of the reaction. And but now, so it's very simple, very straightforward, very clear, and actually consistent with experiments and the observation. Now add one water. How does water change this pathway, if at all? And so by adding water, now, yeah, water can complex with OH, it can complex with HCl, it can actually, you know, form very strong binding complexes along the reaction path, and it actually does change the pathway. So this pathway here in black is the original one without the water, and now the pathways in blue is what happens now when you add one water. And what you start to really see is that there are two new pathways here where the water has actually lowered the barrier, actually falling below what the reactant starting reacting energy level would actually be. So essentially what you will start to do is see, and what you should see in the kinetics is that the water is going to be accelerating that reaction. And indeed, when you look at the kinetics and the rate constants, for this OH plus HCl reaction with and without water, you see a negative temperature effect, and with the water, and without the water, you see traditional, Archimedes kinds of behavior. And actually, the overall rates can be accelerated by as much as a factor of 20 here. So here's a case where the water can impact significantly the kinetic behavior, as well as the kind of reaction pathways to the products that you see, and the consequences acceleration of the reaction. And so one of the things that we found in this particular case, uh, water is found to be, that it can actually reactivate the chlorine through reaction with OH plus HCl. And if you increase the water vapor concentration, you're going to actually decrease the threshold temperature for executing chemical conversion from the stable forms of chlorine to the free radical forms. So now a question that, we start to see, and we examine several other, reactions, elementary reactions, and the water effect on that. And we start to see, some of that. The question we asked is, could water have an autocatalytic effect on some of the reactions? And the number of autocatalysis processes in the atmosphere are actually kind of small. But boy, if it does happen, it could really be impactful. And so one of the things that we all went and tried to do was to look at, are there examples of autocatalysis processes involving water that could be taking place in the atmosphere? And actually we discovered that the mechanism and the accepted mechanism by which acid rain is actually produced provided an avenue where there could be some autocatalysis as enhanced by water forming complexes within species and the acid rain mechanism. So the acid rain mechanism is kind of summarized here, where you have OH reacting with SO2, and that forms an HOSO2 radical intermediate. And that radical intermediate reacts with oxygen very rapidly to give SO3. And the SO3 can react, not react, but actually, in this case here, is suggested to react with water to give sulfuric acid. Now, this last step is actually very slow. It's really all about the hydrolysis of SO3 to sulfuric acid. And the reason why it's very slow, it has a significant barrier for one water. And so you need an extra water to kind of really assist and basically catalyze that reaction. And so here's the one water, then goes to kind of this sort of four-centered transition state. Here's now with two waters, and you're getting almost a 1, 2, 3, 4, 5, 6 centered, transition state, in this process here. And actually, the barrier without any water is close to about 30, 40 kcals. But now that extra water just really drops it. That extra water really drops it. But now the question is, the following. With this water interacting with this SO3 and forming this and forming a complex, are now with forming two two complexes. what now if we have this SO3 with water, and now if you had sulfuric acid that you've generated somehow, and now that too can now take up a water, or that too can now interact with an HO2 water complex, either sulfuric acid with water interact with SO3, or the SO3 carrying the water. If it sees a sulfuric acid, you know, what can happen is now that sulfuric acid can work with that water to autocatalyze, and autocatalyze meaning I'm now going to take that SO3 and use that water to generate another sulfuric acid, which is a mirror image of itself. So it basically converts an image of itself in the process. And being able to do that is really very facile and a very downhill process, whether you use one water or even another sulfuric acid, you know, in its place with the water in order to kind of do that. But now this gets us into, you know, an important question as what we were learning about, you know, water being important and gas phase water being important in catalyzing reactions and autocatalyzing reactions up in the atmosphere. What happens, you know, when a cloud is present? And a cloud is nothing but, you know, a collection of mini waters. And I like to think of a collection of many dynamical waters, which means in that cloud droplet, there's a lot of water and a lot of movement of water and activity of water. You know, what does it do? And so in the earlier days, you know, there was a big effort really getting at really trying to understand uh, what, uh, you know, how does a particle from the gas phase interact with an aerosol or cloud droplet surface? So two things can happen. If a particle from the gas phase saw a droplet, you know, it could hit it and bounce back on off. Or one thing it could do is to hit and get accommodated into the interior of the droplet. So the view at the time was the chemistry, you know, in this environment was either gas phase chemistry or bulk chemistry. So, i.e., what kind of bulk chemistry, you know, and usually acid-base chemistry is going on inside the droplet, and solution chemistry, or what is the gas phase chemistry. But we kind of got curious about what happens here. You know, when it hits this interface, what does it do? And how does it start to diffuse on into the droplet? What is the mechanism, you know, by that? And when I was president of the ACS, you know, I was actually away from the office quite a while, uh, doing the business of the society, until I got a call from the dean of the College of Engineering, wanting to know what my group members were doing using all the computer time at Purdue University. And of course, when I got back to campus and talked to the group and try to really see what they were doing, they actually did something fairly cool, and it was actually very profound and actually a paradigm shifter, you know, at the time. And it opened up some new questions and opened up new doors and directions, you know, around what happens to chemistry on cloud surfaces. But what they did was they decided to take a 20 water molecule cluster, uh, and uh, and what they decided to do is take HO2 radical and bring that HO2 radical up to that surface of that cluster. And as they were bringing that HO2 radical up to the surface of that cluster, and what they were doing at each point, optimizing the entire system except along the coordinate or the HO2 from its center mass to the center mass at the top of the droplet. And this is kind of representation. And then, of course, it fell into a little bit of a well. And then, of course, as you're trying to push the HO2 into the droplet, interior droplet of the 20 water molecule cluster, there's a fair amount of water reorganization. And what that meant is a kind of a high energy cost to reorganizing all those waters. But what was curious about was what is that, this minimum, and what was going on here, and what did that look like? And actually, what that looked like was really very fascinating. It looked like HO2 was happily sitting across and happy to be at the interface of the cloud droplet surface, not on the interior, but at the interface, and it kind of sit happily across two waters. And it sit happily across two waters in a very strong way. Now, remember, experimentally and theoretically, we showed that HO2 forms a double hydrogen bonded complex with one water with a binding energy of 6 kcals. Here it's formed a double hydrogen bonded complex with two waters with a binding energy close to about 12 kilocalories, very, very strong. And what that meant is that these radicals, when it encountered a cloud surface, it will collide and stick. And so now the question is, what is the consequence of that, of this radical sticking to this surface? And now and by the way, I should just say this work was done purely ab initio, and that was one of the reasons why it took a lot of time and computer time. It was just from first principle, physics modeling that. We actually joined forces with a colleague in Japan, Marita, doing some first MD simulations, looking at how HO2 would collide with a rectangular box of waters containing 200 or 300 water molecules to see, if the HO2 accommodation matched that or collaborated what was observed by my students ab initio. And one of the things that we found from that work, and that work was published in Journal of Geophysical Research, that every time an HO2 collided with that surface, it stuck. And there were actually very few HO2s that were released back into the atmosphere. This is roughly, I think, about 1,000 trajectories that were run. And you can see that there really were not many HO2s released. Well, the interesting thing on that, and the exciting part of that, was what it started to point to. Now, when you put this new information into atmospheric models and then run out what the impact of this new observation would be on chemistry of HO2 and OH, what we start to see, and surprisingly, that there was a significant heterogeneous impact by the presence of clouds coupling with that of the gas phase. And actually was able to kind of resolve and describe some of the discrepancy from some of the field measurements work. So now it really started to look at getting us to look at the effects of water at a cloud water droplet interface. And I'm just going to give an example of CLO radical as an example. So CLO will react with itself to give chlorine dioxide, and that its photolysis releases chlorines that actually goes and destroy ozone. And that turns out to be a very important chlorine catalytic oxidation, catalytic ozone destruction process. So our question was, down in the South Poles, we know that there are clouds during the spring, and some of those clouds are quasi-liquid, quasi-ice. Could the CLO be interacting with those clouds? and what would be the impact. Of course, what that meant was first understanding the chlorine oxide can form complexes with water. And this is actually some work that my students did. In fact, one of my students is on the former students who actually worked on this, is on the faculty at Eastern Carolina University, Yu-Ming Lee, and I want to really acknowledge some of her important and early contributions to really developing this picture. But as we do the MD, looking at how CLO, when it approaches the water surface, we do see it interacts, and we see that it will actually bind at the interface. And now what does it look like? And that was kind of surprising, because now what it meant, what we see is all those chlorine oxides, when they hit that water surface, the oxygen part is going to embed itself within the water network, exposing the chlorine part upwards. So now if there's any chemistry is not going to happen at the oxygen part of the molecule. It's going to happen at the chlorine part. And everything we knew about the gas phase chemistry, all happens at the oxygen part. But at the interface, uh, that oxygen is protected. That oxygen is protected by the water network, and it's going to force the chemistry at the chlorine site. And so now what we start to see was some of the first examples of how the interface and water interfaces of clouds or aerosols starts to orient radical species. And that orientation at the interface will change the course of reactions or favor certain reaction pathways that normally would not be followed if that reaction was taking place in the gas phase. And this is certainly an example here where now if another CLO came in from the atmosphere and encountered a CLO in the water interface, it would not be forming chlorine dioxide, ClOOCl, but some of these unstable chlorine oxide dimer isomers whose photochemistry will lead to reintroducing chlorine back into the atmosphere. And actually, this work actually explained some beautiful experimental work that was coming out of Germany, as well. Well, one of the things I wanted to kind of do is kind of also what was very popular and what was very interesting is some new chemistry happening down in the troposphere regarding Kriege intermediates that resulted from reaction of ozone with unsaturated hydrocarbons. And the question is, what do these Kriege intermediates do? And of course, what people thought was Kriege intermediates, since there's so much water vapor, and the water vapor down in the troposphere will kind of really dominate the loss of Kriege intermediates from other chemistry. But people were finding that that chemistry was really kind of slow with a reaction with one water. And of course, eventually what people started to discover is that with water dimer, that chemistry was important. But we asked the question, in the presence of a cloud, and if Kriege actually hit a cloud droplet, what happens to that Kriege at the air-water interface? And this is one of the things that we started to find is that Kriege reaction chemistry, when Kriege hits a cloud water interface, is accelerated. In fact, it's even faster than the chemistry, gas phase chemistry with water dimer. And this kind of pinpoints, and we see that the time scale for reaction at the air-water interface is about 3.6 picoseconds, kind of 4 orders of magnitude shorter than the gas phase reaction. So there's considerable acceleration of reactions at the air-water interface than what you would see at in the gas phase. Now I'm going to just talk over and then try to bring the talk to a little bit of conclusion. So you can now look at how the interface orients, how the interface change pathways, at the same time too, how the interface accelerates reactions. But what about photochemistry? Because if now these radicals actually are stuck on the interface, and not only just radicals, but other atmospheric species, when they see a cloud, they will stick. And if they're there for a considerable amount of time during sunlight, what happens? And does the does the interface change aspects of photochemistry? And the answer to that question is yes. And the yes comes from the example here of looking at ozone. And we know that ozone photolyzes with wavelength about 310 nanometers to give oxygen atoms, reacting with water to give OH. But what we find is that when ozone sees a cloud droplet surface, that ozone is going to stick onto that surface. Some of it goes into the bulk, but the bulk of it likes to stay at the surface. So now the question is, how the electronic properties of this ozone molecule altered by so many waters. Actually, we can think of it being solvated at the air-water interface. How's electronic properties change? Well, what you see here is that through this blue line here, these are the, well, first, the dark line here is the absorption band of ozone in the gas phase. And the blue line is now what the ozone absorption band would be at the air-water interface. And so you can see significant shifts and enhancements of intensities, as well. And this actually goes about really enhancing the photoactivity of ozone at the air-water interface than what you would see in the gas phase from ozone. And this kind of just works through some of that kinetics. And this kind of gives a sense of that enhancement, almost 4 orders of magnitude enhancement. So what that really means is that something that we have really not paid much attention to and didn't really realize before is that these cloud water droplets may actually have considerable, at least during the daytime, may actually have considerable amount of OH being produced on that surface. And as a result, the photochemistry of ozone on those surfaces may actually be turning those cloud droplets into little micro chemical reactors that can basically help clean up the atmosphere perhaps much more effectively than just OH being produced in the gas phase by itself. So we walk away from this actually seeing that on a cloudy day, on a rainy day, it's a good thing because that could actually be going a long way in terms of also enhancing the cleanup of a lot of pollutants up in the atmosphere. So what have we learned? Well, yeah, water is important and clouds are important. And there's much more chemistry going on the surface of clouds than we had totally imagined. And with that, I just want to thank my colleagues and students from many, many places who joined forces to kind of help us to understand a lot of interesting new details and the paradigm shifting of this research, starting at Purdue, colleagues in Göttingen, colleagues in Nebraska, Wisconsin, JPL, UC San Diego, colleagues at Pacific Northwest Laboratory, and my dear colleagues in France and also Spain. And with that, I want to say thank you. Questions?
Thank you, Dr. Francisco. That was great. I have a newfound appreciation for water and its capability to react in the atmosphere. We have some questions. Let me read them to you, and and then you can answer as long as you need. So the first one is from Vincent Esposito.
Yeah, it's my student.
Ah, well done.
Hey, Vince, you're listening. Great.
So he says, hello, Joe. Is the autocatalysis of the SO3 plus water a seeding process for the creation of sulfate aerosols?
Yes, indeed. Yes, indeed. And the answer is yes, indeed. And the question, also now kind of does, as it's seeding, it could actually be converting. So, as the SO3 picks up water and produce sulfuric gas, and there's sulfuric acid can pick up waters, it's actually generating more sulfuric acid, which acts more of as a seed, and they go and pick up more SO3. So in the process of seeding, it's actually using SO3 to, just grow itself. So it definitely, indeed, and that's the kind of the cool thing about this autocatalytic process that we discovered.
Thank you. Other questions from the, I actually, let's see, we've got, hang on, I'm trying to read this. Do you anticipate the newly formed OH radicals from ozone photolysis on the surface of cloud water droplets to stay on the surface of the droplet, sink into the bulk, or be released into the gas phase?
Yeah, so what we find from MD simulations that it doesn't want to go into the bulk. It will actually stay at the interface until it encounters something from the gas phase to react with. Now, one thing I didn't talk about, and this actually came from some later works running the simulations longer times, you can actually have some of these cloud droplets evaporate. And so in that evaporation process, you'll get some release of OH. And so, but there's going to be some kind of equilibrium going on in that process. But for the bulk of the time, what we're seeing is that the OH is going to be generated on that surface and ready to react. And in fact, the waters on that surface will enhance the reactivity and removal of these RH reactions.
Thank you. I wanted to mention that was from Leah Dodson, D-O-D-S-O-N. And everyone who's in the audience, if you have questions, please, on the bottom, you should see a Q&A. So please type your question in there, as opposed to the chat room. And then we did send out a survey about the seminar in the chat. So please complete that at some point before the seminar is completely over. I had a question, Dr. Francisco, if I may ask you.
Yeah.
You know, in geochemistry, we tend to consider budgets and reactions and how reactions affect budgets. You know, from a historical perspective, based on everything you've showed us, it seems like before some of the chemistry your group did, there must have been some wonky numbers for atmospheric budgets for some elements, and there must have been some missing pieces of things that didn't make sense in terms of atmospheric reactions in the troposphere. Or did nobody really look at it that closely until your group started to really look?
Well, actually, yeah, there are some things that didn't make sense, but with so many reactions, you have so many parameters that you can play with. And, so with those parameters to play with, were they actually suggesting that there were other reactions whose reaction rates needed to be studied with, greater detail? And that's what that was kind of pointing to. But I think the key work was Stan Sanders' group at JPL, getting into looking at the water effect more systematically and more detail, that really pointed that there may be something to other reactions being impacted by water. So I really have to give some of that credit to that JPL group's detailed studies.
Thank you. We have another question from Yu Hao. And this question is, if the situation at the water-air interface is similar with that on the cloud surface, sorry, is the situation at the water-air interface similar with that on the cloud surface? I
Yeah,
think that
so
makes
the
sense.
answer is yes. The answer is yes. But you know, if he's asking the question, you know, if we look at a real cloud surface, and what I mean by a real cloud, that the cloud actually has contaminants, you know, versus you know, an air water, which is dealing with pure water. You know, is that situation different? Yes, it is different because now you have another, you know, competing species that you got to kind of figure out, you know, where is it? Is that species going to be in the bulk? Is it going to be at the interface? Now, how does that compete with any, you know, competing processes? But for these studies, we really focused on just a pure water droplet without any contaminant in it.
Thank you.
Thank
Other
you for such a
questions?
great talk. I think that Joan Wiley has raised their hand, and so I'm going to allow them to talk to ask their question.
Go ahead, Joan.
I have really enjoyed the talk. Thank you very much. I
You're
didn't
welcome.
really have a question. I was trying to fill out your form.
Oh, okay.
So thank you. I've been reading your
No
work for a
problem. Oh my goodness. Okay. Thank you so much. I really appreciate that.
I want to just state that Joan is the pioneer of rainwater chemistry and carbon in rainwater in you know, North Carolina, perhaps the world, one of the pioneers. And she has really created and developed a huge group of other chemists who've been studying rainwater chemistry using a site in coastal North Carolina near UNC Wilmington. I believe, Joan, you're retired now somewhere in Canada or New England somewhere, right?
Yes, well, thank you, Sid, for your very kind words. I am retired, and right now I'm in Maine with my son's family.
Yeah, so Joan is quite the pioneer. It's great to have you listening in, Joan. Thank you for joining.
Thank you, Joan.
Thank you. This is a great topic.
Thank you, Joan. And Joan, I'm glad you kind of and thank you for introducing Joan, because Joan, I want to kind of introduce a little bit of a punchline, and the punchline that I forgot to mention. So you know, in our work, what we're discovering is that there are really three regions of chemistry going on. You got your gas phase chemistry, and then you got your solution-based chemistry inside the droplet, and then you got your interface chemistry. And you know, your gas phase chemistry will not describe what's going on that interface, because of the alignment that interface is doing, and changing that alignment changes pathways, but at the same time too changes the acceleration of reactions as well. But once something gets into the bulk, that solution chemistry dictates. So what happens at the interface can't really be, solution chemistry can't really explain the chemistry at the interface either. So what you have is really now three regions of chemistry that you have to think about. Certainly chemistry in the gas phase, the solution chemistry, but also the chemistry at the interface when we're looking at a cloud droplet interacting with species in the atmosphere.
Well, that's a very interesting point.
Mm-hmm. Mm-hmm.
A lot to think about.
Other questions from the audience? I think that is all we have as far as questions. We had quite a few people joining in. If there are no other questions, I'd like everyone to thank Dr. Francisco again for his time. I don't know how we do thank you on these virtual platforms. So,
That's okay.
Well, I think everyone would applaud if they could figure out how using their computer.
Welcome.
And I want to thank Malcolm again for his inspiration to start this seminar series. We will be doing there'll be a few other speakers between now and the end of next spring. So stay tuned. I'll be sending announcements out, and ACS will also be, we're going to try to get back to some safe programming, some social programming, but safely. And so stay tuned for that. And other than that, I will bid everyone a good night and thank Dr. Joseph Francisco again. And please fill out the survey if you haven't done so already about the seminar.
And everyone, be safe and stay healthy. Take
All
care.
right.
Now.
You too. You too. Good night.
Thanks everyone for joining.